Welcome to lecture 3, and in this lecture we're going to talk about Newton's law of motion. So the Newton stated that the net force is equal to the sum of mi and times ai, and this acceleration vector. And for a simpler case, we're just going to consider a mass that is like away from all the interference except one force, which is F. So Newton stated that the acceleration, so dv dt of this object is basically equal to F divided by m. And some may like write it in this form, which is also kind of fine, but I don't really like it because there's changing mass, so it kind of looks weird. Okay, moving on, and we're going to see how this works. So basically, if you consider two objects, and there are force like acting on each object, which is friction, by the Newton's third law, which stated that every action has an equal and opposite reaction. So basically, like this force has a like the magnitude of this force are the same, but the direction is the opposite. So basically, and there's an external force in the system, and in the system you consider, if you sum all the forces, like you can get like mi ai is equal to sum of all forces, which is the same as Newton's law. And you can see in the system, like this kind of forces just cancel each other out by the Newton's third law, because like opposite direction and same magnitude. So for example, if a block like here is moving to the rightward, you will experience friction force, and the block at the bottom will experience a friction force pointing to the right. Okay. So, and if we have an external force over here, the Newton's second law is going to be written as a form of mi ai is equal to sum of all forces, which is F minus F and plus F. And you can see these two forces cancel each other out. So by similar case, if we consider a system of n objects, and they might exert like electric force to each other, some kind of this, you can see like all the forces of the internal system cancels each other out because of Newton's third law, and the only thing we need to care about is the external force. So basically, we can write mi ai is equal to F is equal to F internal plus F external, and this is equal to 0. And this one we can just write it as a big F, which proves the formula over here. And the second topic we're going to talk about is the constraint of the string. So in a string, you learn that like the tension in of a massless string is 0, but you actually don't really know why. So I'm going to teach you guys why. So if you consider a small piece of the string, which the length is dx, and it will like experience force of t, like tx, and here is tx plus dx. And because this stuff is massless, so if we write the Newton's second law, we can't have Tx plus dx minus Tx is equal to dm times a. And if you divide dm over here, and we know that tension is quite large, but the dm is really small. So you will have that this is just approaching infinity, which is very large. So in a short time, if the string has mass, like you will have the velocity like approaching infinity, just in a short amount of time. So we must have something like Tx, and Tx plus dx must be equal to each other. So the string, small part of string will have no acceleration. Okay. Thus, we know that tension in each part is the same for a massless string. This one is case 1. And going for the pulley, like if you have pulley over here and experience the force, and I'm going to show you like the tension on two sides is also equal to each other. Okay, if we have a circle over here, oh my god, wait a second. And we want to analyze this part, like from theta to theta plus d theta. Theta, d theta. And we can see that the tension is perpendicular to this part. The tension over here is perpendicular to this part. And if we draw a line over here which separates the two, and we can see that, wait a second. We can see that the angle between the tensions is d theta, because it is just turning like this. If you have the bottom like turn like a certain degree, this one will also turn a certain degree. So the difference is the same. I'll show you guys. Yeah. So the difference is the same. And for like in the tau direction, which is the tangent direction, we have the tension to be like by small angle approximation over sine theta is approximate to theta. So this part is d theta divided by 2, and this part is d theta divided by 2. So basically we have that t theta plus d theta sine d theta divided by 2 is equal to t theta sine d theta over 2. And these two terms cancel each other out, which leaves that t theta plus d theta. What I'm doing? Wait. This one is tangent. So basically, we have t theta cosine d theta divided by 2 is equal to t theta plus d theta is equal to cosine and d theta divided by 2. We can see this term just approaching 0 when it is getting very small. So cancel, which also get us to have t theta is equal to t theta plus d theta. So we know that the tension on the pulley is the same. So this side's tension is equal to that side's tension if there is no friction on the pulley between the string and the pulley. In this case, mu is 0. And for like most of the case, we consider mu as 0 in many problems of in the F equals ma competition. And we'll talk about like how the tension are different if there is like friction over here. We're just going to talk about it later. Okay, we're going to talk about the frictitious force. So basically, if you have like two systems or two coordinate systems, okay, this x, y, z, and you know that x cross y is equal to z. It is like we define it. The direction of the z is equal to x cross y, which is your 4 fingers, and bend is outward, and here's the direction of the thumb. Okay, let me copy this. Wait a second. And here is another system which has coordinate system x, x, y, z prime, kind of like that. So the relative displacement vector is r1. I guess you can call it r1. And so if we describe a point using the new coordinate system, we can see this is basically going to be equal to like r2. Just treat it as r2. I don't know how to pronounce this stuff. So in the original system, we can see this can be represented as r. So let me write it out. R is OO, and R is a vector in the new coordinate system that describes point A. We call this point A. And R is a vector that describes point A in the coordinate system of S, or just frame S, and this one's S prime. I don't know how to say it. So basically, you can see that from vector addition, which is like the R describing the frame of S is equal to the relative like displacement of S and S prime, and plus the displacement of the A describing the new frame of reference. And now if we take the integral, we have that dr dt is equal to dr prime dt plus dr double prime dt. So basically we have that the velocity is equal to like O, the relative velocity, and the velocity of A in frame of S prime. Remember this fact, it's pretty important. So if we take the integral again, we can see that A acceleration is equal to A OO plus A relative. And now if we time m by both sides, plus A relative, we can see that like we define this as a force. Like, wait a second. And if we move this side to that side, and we have ma minus ma this ma prime is equal to ma relative. And you can see that we can treat it as a new force, which we call the frictitious force, which has opposite direction as the frame direction of the acceleration s prime relative to s. To be more straightforward, like if you have a car over here and we treat it as s prime frame of reference, and here is the ground, and it is accelerating at a like prime. So the frictitious force we experience in the new frame of reference is basically opposite to the direction of the acceleration. So if we put this in a non-inertial frame of reference, I'll explain what an inertial frame of reference is, just to clarify. So for non-inertial frame of reference, Newton's second law works, and the other physical phenomena it's also the same. It also works. We can treat our galaxy system as a inertial frame of reference because there's little external force acting on our galaxy. So it is not really accelerating or something, so we can treat it as an inertial frame of reference. And often we treat Earth as an inertial frame of reference because its acceleration is quite negligible in sometimes, only in some circumstances. And you can search this term up on your own if you want. I recommend you to do that. So basically, if here's an apple, and we drop it from the car, and we want to describe it in the frame of the car, we just put an inertia force on it. And basically, in the bus frame of reference, the car is still, and the apple is dropping, and which experience and gravitational force and a frictitious force pointing to the left. So basically, this frictitious force is useful when describing physical phenomena in the accelerating frame of reference. So another example is that when you're driving, you're turning to that side, you'll feel you're being thrown to that side. So basically here is an example of the frictitious force you experience. It is not real force, but it is a force that you can invent to describe phenomena in the acceleration frame of reference. So now we're going to the rotating frame of reference, which is the first we need to introduce W and beta. So for W, it is basically d theta dt, and beta or alpha You can write it alpha or beta, I don't care. So beta is just basically dw dt, which is d double prime zeta dt. And by the we define the direction of the this vector of the omega vector as to using the right hand rule. So if you have your 4 fingers over here, just bend it around the circle, and the direction of the W is the same direction as the sum. So if you have a clock rotating over here, you know that it is rotating to here. So if you bend your 4 fingers, just use your fingers, you can see that your sum is pointing inward. So that is the direction of the omega vector. And now we're going to describe. We're moving on to a simpler case where we analyze the force experienced by the object when omega is the same. So basically this is rotating with the same angular velocity over time, and we want to find out the amount of force it experienced. And by the definition of force, which is dv dt, and we can see that v is also is changing direction. So there must be a force acting upon it. So if we draw the diagram over here, here's here, and d theta. We know that because w is constant, so we have that velocity. The magnitude of the velocity is also constant. If we put the vectors in the triangle, we can see that when delta t approaches 0, d theta is also approaching 0. And because it is perpendicular, you're just rotating this. So you can see the angle difference is the same for this, and this. So basically here is also d theta. Let me erase it. And we can connect these two vectors, and this is changing velocity vector. So when delta t is approaching 0, and we can see that this vector, it is just going to, the magnitude is just going to be r or v d theta. Wait, v d theta. Okay. And d theta, by definition, w is equal to d theta dt, so d theta is basically w dt. So this stuff is equal to, let me check. V w dt. So the acceleration vector is basically vw. And the direction, we can see that when d theta is approaching 0, this is basically pointing to the center. So the acceleration is pointing to the center of the circle. And the condition is when w is constant. You need to know that w is constant. the condition is W is constant. And we know that like the way you find arc length is just time the radius by theta. And so you know that ds dt is basically the velocity, and this can be expanded out as dr theta dt, and we know that the radius is constant in this case, so basically it is equal to r d theta dt. So the velocity at this point is basically wr, like the magnitude. And the physicists write the velocity in this form, and you can see why. Like in this coordinate system, and it is rotating in this direction, and here is a r. So basically, if you make a perpendicular a vector that's perpendicular to the z direction, and you can see this is just basically equal to w r like sine. So this is basically this, and you can see that like the velocity in this case is just same as the velocity in this case, and thus this equation works. Just remember this fact, it's quite important. Let's write it down here. V is equal to W cross R. And from here, we know that W is equal to VR, so this is basically V squared R, and this is also equal to V W or omega squared R. Okay. And if omega is changing, we're going to describe the. We're just going to see in a second, okay? If we draw the vector over here, and draw another vector, and at this moment, the velocity is v, and at next moment, the velocity is just going to be v plus beta r dt. I'll show you why. So basically, like dw dt is beta. So dw is equal to beta dt. So dv is equal to v. So dv is r dw, which is equal to beta r dt. Okay, now we also can draw a triangle over here. And in this case, d theta is also very small, and so we can separate it into the tangent, and this one is the tangent direction, and the direction of the r. So basically, like if you have a vector over here, this is a tangent direction, and this is like direction of the displacement vector. So now you can see the change in this is basically beta r dt, and because this is very, very small, you can see this side are just basically equal to each other, so which is omega r, right? Okay, let me see. Yeah, this side is omega r. So basically now we can, like here, we can see that we can separate the changing velocity as two components. This component and this component. To center, tangent to center. And if we divide dv by dt, we can see this is just going to be beta r tangent and minus w squared r and this represents as a normal vector which has magnitude of 1, and the direction is pointing to the tangent. And this one is a unit vector. This one is a unit vector, and this one is a unit vector, which all have the magnitude of 1, and the direction is this one is just direction of the r. And this one is also equal to a. Okay, moving on. We're going to talk about the force experiencing the polar coordinate, and this one is quite exciting. This one is actually quite interesting. Okay, let me draw the graph here. R and RT, and this one is RT plus DT. And we separate it into the tangent, and this direction is the direction of the r vector, the displacement vector at time t. And here is a change in r, dr. So this one is dr perpendicular, and this one is dr parallel. And you know that d theta, so this is basically r d theta, is the magnitude of this is basically dr, it's basically dr, changing the radius. And we know that it is also dr dt times dt. Okay? And the direction of the change, if we d theta is getting really small, it is just the direction of the r. So it times r, and this direction times theta. Oh, we need to define this something. This unit vector is just basically perpendicular to the r direction. So the velocity can be separated into two terms, dr r plus r d theta and the theta direction. And if we divide by t, we can get this is basically dr dt times the direction of the r, and plus r d theta dt and the direction of the theta. It's not the direction of theta actually. Whatever, just direction that is perpendicular to r. So for convenient purposes, we denote it as r dot is equal to dr dt, and r double dot is equal to d double prime of r dt, and d theta is equal to theta 1 dot, and so on. This is basically r dot times r direction plus r theta dot times this direction. And for the acceleration, we just take the derivative. It's quite simple. And by the chain rule, we can see this is equal to r direction plus r d this, and dr dt plus r double dot plus r single dot dt. Okay, we're going to see how to evaluate this stuff. from the graph over here, this is annoying. Really messy. This is changing the R. It's R in PDT, and this is R in time t. So if we put in a triangle, because it's a unit vector, it has magnitude of 1, and the change in direction is basically pointing to the R direction, to the theta direction, and the magnitude is basically just like it is just same as like the arc length of a circle. Which is equal to like magnitude of 1, and d theta in the direction of this. We can ignore this as this is basically this. Okay. And if we divide by dt, this is basically omega to this direction. This term equal to r dot, theta dot, and times this. And for this term, it's very similar. And if we put it in a triangle, we can see that the change is pointing to the O. The direction of the change is pointing to the O. So it is basically the reverse of the R direction. Similarly, we can see the magnitude is d theta times 1. So, and times this. And if we divide by t, this is basically equal to d theta dt and the R direction. And expand the formula we have and times theta direction, theta this direction, and plus r double dot this plus r this, and times okay. So if we like combine the terms, this is basically equal to r theta squared times the R direction, and plus there's 2 over here, so basically R this and plus this term, and times the theta direction. Okay, I'm kind of tired, so I will explain the rest in the next video. Okay, bye. And also, this stuff is not really important, but it's really helpful to understand concepts. Okay.